Hi, we just reviewed some concepts about eigenvectors and eigenvalues from linear algebra. But in general, to find the eigenvalue is not easy, right? For a 3 by 3 matrix, we need to solve a polynomial equation of degree 3. And in general, the roots might not be rational roots. Okay, and then after we find the eigenvalue, we still need to use the Gaussian eliminations to find the eigenvectors, right? So now today we're going to talk about a power method. So the power method is an iterative procedure for determining the dominant eigenvalues of a matrix A. That is, it only tells us the eigenvalue with the largest magnitude, not all of the eigenvalues. For example, if for a 3 by 3 matrix, maybe its eigenvalue we have like 24 and 1 and 2, and then this method can only tell us the largest eigenvalue. Eigenvalue with the largest magnitude. So even though maybe the eigenvalue is negative, then the power method will tell us this guy, okay? And we don't know the rest, so we don't know it for the rest. It only tells us the eigenvalue with the largest magnitude, but not all of the eigenvalues. So the basic idea is that the defining relationship, which is satisfied if x is the eigenvector of A. Okay, so we have ax equals lambda x can be converted into a sequence of approximations to lambda and x. So we start with an initial guess z for the eigenvectors x, and we compute w equals az. And usually this z is the vector 1, 1, 1, 1, 1. Okay? You might ask, can we use the zero vector? No. Because if you start with a zero vector, a times 0 just 0. It doesn't help, okay? So don't use the zero vector, it won't help. Okay, so we start with the initial guess, that's 1, 1, 1, 1, 1. If this vector, if z is an eigenvector, then we have w equals lambda z, right? Then we can use this information to solve lambda. While because they're scalar multiple of each other, we can just pick one component of w, use it to divide it by the corresponding component in z, and then to find this factor, lambda. If z is not an eigenvector, we would like to use w as our next approximation. Since an eigenvector is determined only up to a scalar factor, we can actually normalize w to give the next approximation. Especially for hand computation, it is convenient to normalize so that at each step, the norm of our estimated eigenvectors equals 1. And here we use the L infinity norm. Do you remember the vector norms? We learned L1 norm, we learned L2 norm, which is the same as Euclidean norm for vector norm, okay? But for matrix norm, there are different norms. And also the L infinity norm. So let me review with you. L1 norm is the sum of the absolute value of each component. L2 norm or Euclidean norm for a vector is the square root of each component squared. And L infinity norm is the maximum of the absolute value of the coordinates. Okay, which means we get the largest component. Okay, so that after we normalize it, this z, we have the L infinity norm is 1. It means the largest component of this new vector z is 1. So suppose the component of w that has the maximum magnitude is wk. So k here is the index of the components. If A is a 3 by 3 matrix, then the index, it could be 1 or 2 or 3. Okay? So the procedure is as follows. I make it into a table so you can see in each step what are the eigenvectors and what are the eigenvalues. I mean the estimates eigenvectors and estimate eigenvalues. The first step, our estimate of eigenvector is z1 we define to be 1 1 1 1 1. I just use this notation to save some space, but you know this is a column vector. Okay, that's why I put a row vector and then transpose to make it into a column vector. Then W1 is A add on this Z1. Okay, and then WK1 is the largest component. So this is the largest component of W1. So far, so good, everybody? Okay, next. Z2 equals 1. So the W1 over, this is the L1 norm of it. So now the norm of the Z2 is gonna be 1, okay? And then W2 is A's add on Z2. WK2 is the largest component of W2. So this is a number. It is also the L1 norm of the W. Sorry, L infinity norm of W. Okay, and then Z3 is W2 over this WK2. Okay, so this is like the normalized W2. And W3 equals A times Z3. And then we find the largest component to be WK3. By the way, these K's might change. Maybe in the first step, your first component is the largest, then you have W1. And in the second step, your largest component is the second coordinate, the second component, then this K changed to 2. And maybe the third step says the second component is the largest. So the index may change. Keep in mind with that. Okay, let's continue. Analysis. Now consider how the iterate depends on the matrix A. Then we can get this. So first step, we have our eigenvector. The estimated eigenvector is Z1. That's 1 1 1 1 1. W1 is A's add on Z1. And then Z2 is AZ1 divided by WK1. So this is just a number. Okay, so W2 is A add on Z2. So this is the same as A squared add on Z1. Okay, divided by another number. And then Z3 is this guy divided by WK2. So divided by another number, which is the largest component of W2. Okay, and W3 is A add on the Z3. So now you can see this. Here we have A cube, and here we have A squared. Here we have A. So carry out the iterations has the effects of multiplying the original estimates by successively higher powers of A. That's why we get the name of the power methods, because the higher powers of A, so we call this method power method. So far, so good, everybody. Let's do some example. So keep this in mind. By the way, this table will be provided in the exams. Okay, so let's follow the steps. This is our A. We want to use 3 iterations of power method to estimate the eigenvalue and eigenvector. Okay, so eigenvalue of the largest magnitude and the corresponding eigenvector. So step 1, the estimated eigenvector is 1 1 1. So this is A is a 3 by 3 matrix. So Z1 is 1 1 1, and W1 equals A add on Z1, and equals 21 7 minus 1 5 7 7 4 minus 4 20. Add on 1 1 1. So how do we calculate? Well, we use row times column. 21 times 1 plus 7 times 1 minus 1. Okay? And then 5 times 1 plus 7 times 1 plus 7 times 1. 4 times 1 minus 4 times 1 plus 20 times 1. So far, so good. And 21 minus 1 is 20. 20 plus 7 is 27. And then 7 plus 7, 14. 14 plus 5, 19. 4 minus 4 is gone. And so it's 20. So far, so good, everybody. And this guy is the largest. Right? Because this guy is largest, we say the W1 norm, L infinity norm equals 27. And this is W1 of which component? This is the first component. Okay? So this is the first component of W1. Okay? It has largest magnitude. Sometimes it could be negative. Okay? So we just look at the magnitude. The magnitude is largest. So far, so good, everybody. So that is the first step. We get the estimated eigenvector and the estimated eigenvalue. Okay, second step. So Z2 is then the normalized. Okay, so W1 over the norm of it. The norm is 27. And W1 is 27, 19, and 20. Okay, 27 over 27, that's 1. 19 over 27 and 20 over 27. Okay, so this is the same as 1. And here, calculator 19 divided by 27.7037. So in this process, it's okay to keep 4 decimal places. Okay? And 20 over 27. Oops. 27. 7407. Okay, so this is the estimated eigenvector in the second step. So then what's W2? W2 is A add on the Z2. So A is 21, 7 minus 1, 5, 7, 7, 4 minus 4, 20 times this vector 1.7037.7407. So far, so good. So here, you can use your graphing calculator. But don't forget, you need to show all the steps in order to receive credit in the exams, okay? But I do allow you to use graphing calculator in your exam. So, I checked this website, and let's pretend this is our graphing calculator. So we input the matrix. So here you can change the matrix size, right? And here, let me type the matrix 7, 7, 4, -4, 20. Okay, now our vector 1.7037. This is 0.7407. Okay, so if you use your calculator, for the first steps, you can first input the vector 1, 1, 1, and then you input the matrix A, and then you let matrix A times that vector, you get a vector, and then you can call this new vector B, and then you can use our matrix A times this vector B, and then it will give you more accurate answers. Okay, but now we only type 4 decimal places inside. Let's see, what do we get? Okay, so this is what we get. Let's copy it down. Okay. So in order to make it so more accurate, let's see. Let me do here. Let me do 19 over 27. Okay, and this is 20 over 27. Okay. All right. It actually gives us fractions. And fractions is good because it's exact number. Okay, so let's keep the fractions. All right. So if we keep the fraction, it's 680 over 27. And next one, 136 over 9. And then 16, right? And we would love to keep these fractions, but because we also need to compare which one is the largest, right? So let me see. Am I able to change this number into decimals? I can't. Okay, let's use our original calculator. So 680 divided by 27. 27. 25.1852. And 136 over 9. 15.1111. And this is 16. Which one is the largest? Oh, of course, the first one. Right? So in this case, W2 our infinity norm equals 25 let's use the fractions, okay? So 680 over 27. And this is W2. And this is the first components. So this is still 1. Okay, sub 1. So far, so good, everybody? So the index K might change. Maybe in the first step, the first component is the largest. Maybe in the second step, the second component is largest. Then you change this number to 2. Okay? All right. So this is the second step. Let's continue. So step 3. So Z3 is then 1 over 680 over 27 of 680 over 27. And then 136 over 9, 16. Okay, so this is the same as all the coordinates. All the components multiplied by 27 over 680. So this is 1. And then the next one. Okay. Let's see here. Alright. So next one, we have 136 over 9. And then times 27. And then over 680. Okay. Oh, the answer is 0.6. And then, let's see. Oops. And then we have that guy. We can just change 16. Okay. And let's see. This is 54 over 85. So far, so good, everybody. Okay, and actually 0.6 is 3/5. Okay, if you want to use the fraction form, yeah, it will be more accurate, then we can keep the fraction form. Alright, next, W3 is then A add on the C3, so which is A 21, 5, 4, 7, 7 minus 4, minus 1, 7, 20, times 1, 3/5, 54 over 85. Okay, now let's see. Our matrix multiplication website. A is the same. B is first component still 1, second component 3 over 5. The third component 54 over 85. Okay, and let's see. This is our answer. 28 over 85. Okay, and next. Oops. What is next? 232 over 17. 232 over 17. And then 1216 over 85. 1216 over 85. Okay, what is this number? Yeah, because fractions, right? Let's make it into decimals, then we can see it. So if you're using your graphing calculator, then you can switch to decimals or fractions as you want easily. So 24.5647. And then 232 over 17. Oops. Okay. Okay. 232 over 17. 13.6471. And then 16 over 85. 14.3059. 14.3059. So far, so good, everybody. Okay, which one is the largest? Well, still the first component in this case. So W3, our infinity norm is 24.5647, and that's W3, and this is the first component. Okay, so what is the estimated eigenvector? Okay, estimated eigenvector in step 3 is this guy. Okay, so that is 1 3/5 54 over 85. So far, so good, everybody. If we want to use the decimals, this is 0.6. What's 54 over 85? 0.6353. Okay, and our estimated eigenvalue approximately equals to 24.5647. So far, so good, everybody. Okay, so if we want to compute the, so let's check our answer using MATLAB. If we input brackets VD, well, this is we get the eigenvalues 24, 16, and 8. You can see our answer is close to the largest eigenvalues. Okay, and oh, you might see, okay, why are they different? Well, but think about it. The eigenvectors, there are a lot of eigenvectors, right? But the relationship of them is like constant multiple of each other. So you can see this is one, right? If you want to check whether they are the same or close, you can use this eigenvector divided by negative 0.8165. So the first component is 1, then you can compare. So far, so good, everybody? Okay, now this is the power method. Okay, next, I'm going to show you how to use MATLAB. Okay, so how to use MATLAB, the power method to estimate the eigenvalue lambda of the largest magnitude. Okay, the syntax is Zm equals power A. This is the maximum iterations. Okay, so, and then we have the tolerance. So here, this is our original example. We can do, so Z is the eigenvector, M is the estimated eigenvalue, right? So let's do 5 steps and let's use the tolerance 0.0001. And this is what we get. Oh, okay. Actually, here I use 10 steps when I input it. So now let's check our answer. See, our first steps, our estimated eigenvector, we start with 111, and then we get to the third step. This is our estimated eigenvalue. Do we get 24.5647? Yeah, see, we get 24.5647. And our estimated eigenvector 1.6 and 0.6353. And here, see, we get 1.6.6353. So our answer agrees with MATLAB. So this is also a good thing for our course. For many type of problems, you can use MATLAB to check your work, so you know whether you're doing right or wrong. But unfortunately, you cannot do it for the exam. Okay, so far so good, but you can check your work for the homework. Okay, so, and you can see here after 10 steps, our estimated eigenvalue is 24.0209, and we know our true value for the eigenvalue is 24. It's pretty close. And actually, if we increase the steps, the number of steps, you can see the power method converge, and the eigenvalue we get 24.0000. So it's super close, right? It converged within the errors within 10 to the minus 4 or 5. Okay, it's quite close. And you can see this is the estimated eigenvector, right? This eigenvector, the L infinity norm equals 1, so which means the largest component equals 1. And you can see 1.5.5, and let's get back to here. You see, this actually match, because this guy and the second coordinate and this first component, the first component is like twice times the second coordinate, and it's also the second component is the same as the third component. So we know this is like constant multiple with the vector 1.5.5. So that's why the eigenvectors also match. Yeah, remember last video we talked about if V is an eigenvector, any constant multiple of V is also an eigenvector. So far, so good? Okay, but however, the power method can only help us to find the eigenvalue with the largest magnitude. It won't help us to find all of the eigenvector and eigenvalues. So far, so good, everybody? So I show you in MATLAB. Let me actually show you in Octave when I actually type this syntax in it. Okay. Alright, so first let's type the A equals matrix, right? So 21, 7 minus 1 and 5, 7, 7. 4 minus 4 and 20. Okay, and our syntax is brackets Cm equals power A. Let's do 100 steps. Let's have the tolerance 0.00001. Oops. Okay, see? The power method converge. And because I do 0.00001, so one more digits. So that's why you can see it takes more steps to converge. So far, so good, everybody. All right. And how about I can also show you how to find the eigenvector and eigenvalues. So we do V D equals eigen of A. So this give us the eigenvectors matrix V and the eigenvalues matrix D. Okay, then we know there are 3 eigenvalues, 24, 16, and 8, and their corresponding eigenvectors. Okay, let's continue. Okay, so here, if the dominant eigenvalue of the matrix is well separated from the next largest eigenvalue, then the power method converges rapidly. So let's look at this example. Use power method to estimate the eigenvalue lambda of the largest magnitude and the corresponding eigenvector of it. Okay, so we type this matrix in it. So we input these, and we can do Zm power method matrix H with 15 iterations, and the tolerance is 0.0001. And this is what we get. See, it converges so quickly. And why is that? Well, you see, these are the eigenvalues. So all the eigenvalues are 10, minus 0.5, and 0.1, and 0.2. Wow, 10 is well separated with the other eigenvalues. So that's why the power method will converge rapidly. Okay, and so here, oops. So let's look at the following example 6. So we also have the matrix H. It's a 4x4 matrix. So we can input this matrix in MATLAB and then use the power method to compute. And this is what we get. Okay, so you can see, wow, after 15 steps, we can still don't get it converged, right? And the last example, we only use 5 steps and it converged because the eigenvalue with the largest magnitude is well separated than the next largest eigenvalue. But in this case, let's look at the eigenvalues. The eigenvalues are 72, 36, 18, and 9. So it's also well separated, but compared with the last example we have 10, and the next largest one is negative 0.5. So the gap between them is much bigger than this one. Okay. So now you can see if the gap is bigger, the convergence will be faster. Okay, and we mark the error is z minus lambda z. So in the above MATLAB notation, we use the Euclidean norm of the error. So for MATLAB, you can see this is R. So the first column is the steps of the iteration, and then M is the estimated eigenvalue, and R is actually the error bounds. Okay, and then we have the Zi's are the components of the eigenvectors. Okay, And how do we compute this R, this error bound? We use AZ minus lambda Z. Okay, and we calculate the Euclidean norm of it. Okay, so in example 5, the first two eigenvalues are well separated, so we expect rapid convergence. So you can see the first one is 10, the next one is minus 0.5. The ratio of them is 1/20, which is very, very small. But in the example 6, the eigenvalues are 72 and 36. The ratio between them is 1/2. So now we can see the convergence should be expected to be slower than in example 5. And we can see it under the same tolerance. Example 5 take 5 steps to converge within that tolerance, that error. But example 6, well, it takes 15 steps. Maybe more than that. We can actually do it here using Octave. Do you want to do that? I can show you. Example 5, we converge in the 15 steps, in 5 steps. Let's see. How about example 6? So let me see when I copy it, does it work? Yes, it works. And then I can just copy this code. Sometimes when you copy it, maybe the format is not good, so you don't get it. Oh, okay, let's see. Let's increase. So let's increase the steps, to 150. Okay, because 15 steps, we actually get 15 steps, but we don't know whether it actually converge. Oh, so 15 steps is not enough. It actually takes 21 steps to have the power method converge within that tolerance. So far, so good, everybody? All right. Okay. Let's continue. Okay, from example 6, we can see that eigenvalue is found more quickly than the eigenvector. Oh, why is that? Okay. And you can see here, the eigenvalue is already very close to each other, but the eigenvector is still takes some time to find the more accurate eigenvectors. Maybe let's look at, if we just look at the four decimal places, then you can see after step 8, our eigenvalues is 72.0000. But for our eigenvectors, so it takes more time to compute the more accurate eigenvectors. So far, so good, everybody. So this is what we mean by saying the eigenvalue is found more quickly than the eigenvectors. Okay, so let's continue. Okay, next, smallest eigenvalue. So the fact, here we have a fact. The eigenvalues of B, which is the inverse of A, are the reciprocals of the eigenvalues of A. So therefore, we can apply the power rule to the inverse of A to find its dominant eigenvalue M. Then the reciprocal of M will give the smallest magnitude eigenvalue, lambda of A. Okay, so for example, this is the matrix we did in class, right? And we can use power methods, apply on the inverse. And let's see what happened. Okay, when we use the power method apply on its inverse, we get the M is 0.1249, and the reciprocal of it is around 8. And the eigenvalues of the matrix A is 24, 16, and 8. And you can see 8 and 8, they match. So now actually using the power method, we can find the largest eigenvalue, and we can also find the smallest eigenvalue. Smallest, I mean the smallest magnitude. Okay, so let me put it down right here. Write it down. Okay, so use power method. We can find the largest eigenvalue. Largest, I mean magnitude. Eigenvalue. And we can also find the smallest magnitude of eigenvalue and the corresponding eigenvector. Okay, but the largest eigenvalues, well, this is a direct way to do it, right? Just apply power method on it. But the smallest eigenvalue, well, you need to apply power method to the inverse of A. Okay, and then you get the estimated eigenvalue M. Okay, then our smallest eigenvalue is actually 1 over this M. So far, so good, everybody? Yes. And let me show you here. So in Octave, let's copy this matrix down. Okay, and yeah, if we do VD equals eigen of A, then we know we have 3 eigenvalues, 24, 16, and 8. And then we can do power methods. So power method, and let's change this to A. Okay, so it converges in the 26 steps, and we get the eigenvalues is 24. So this is the largest eigenvalue, right? But if we use the power methods, apply on the inverse of A, let's see, we get this. Let's increase the steps to get a more accurate answer. Okay. See? 0.1250, and 1 divided by this 0.1250 is actually 8. See, this is the smallest eigenvalue of A. So now power methods can help us to find the largest magnitude. It can help us to find the eigenvalue with the largest magnitude. It can also help us to find the eigenvalue with the smallest magnitude. Okay? So the largest magnitude and the smallest magnitude. So it can help us to find 2 eigenvalues. So that is the power method. We don't need to solve the characteristic equations. We don't need to solve the polynomials and do the Gaussian elimination. We just use the power method. So far, so good, everybody? Okay, so that is the chapter 5 we covered. Okay, so next video we will talk about chapter 6. So please do your homework. If you have questions, feel free to ask me. Cheers! Have a good day. Bye!